Hi everyone, this is Radha Rajeshwari. Today we'll be discussing on spectral clustering algorithm, which is one of the type of clustering algorithm. This is a pictorial representation of spectral clustering algorithm. It is a clustering algorithm which uses connectivity between the data points to form the cluster. For example, if we have data points A and B, if A is connected to B, then these 2 points are used for forming the clusters. It is a data partitioning algorithm. The data points are partitioned based on spectral graph theory and linear algebra. So here the idea is to segment the graph, that is split the graph into smaller groups with nearby values or similar values. Either with similar values or nearby, so groups are formed from the graph. The first step of the algorithm, process of the algorithm. The first step is similarity graph construction. So this graph can be constructed in these 3 ways, either epsilon neighborhood graph, k nearest neighbor graphs, or fully connected graph. Epsilon neighborhood graph. This graph is connected by defining a distance epsilon. Only the pairwise distance between the points are smaller than the epsilon, then the connectivity will happen between the points. For example, if we set epsilon equal to 5 and we have 3 data points A, B, C. A to B we have distance 4 and A to C we have distance 6. Then we will connect only A and B which have smaller distance from epsilon. So by this way, this epsilon neighborhood graph is constructed. The next graph is k nearest neighbor graph. Only the data points are connected when the other point is the k nearest neighbor of one point. For example, we will connect vectors vi, vj only when vj is one of the k nearest neighbor of vi. So this may lead to a directed graph. To make it undirected, either we can connect vi to vj and vj to vi to form an undirected graph, or we can remove the weights. The fully connected graph. The fully connected graph is each point is connected with an undirected edge weighted by the distance. Here, for example, I to j, we have the weight as wij. This can be calculated by this formula. This is fully connected graph. So the first step is graph construction. After that, we will be representing them in a matrix form, matrix representation. The first matrix is affinity matrix. To determine the affinity matrix, we will take the graph. Here we have 6 nodes, 1 to 6, which is connected in this way. From this, we will get a matrix. So we have 6 nodes, 1 to 6. We will have them vertically and horizontally here, rows and columns, and then we will have values zeros and ones based on their connectivity. If, for example, first node 1, if 1 is connected to 1, then we will have it 1. But here 1 is not connected to 1, so we have 0. 1 is connected to 2, we have 1. 1 is connected to 3, so we have it 1. 1 is connected to 4, no, so we have it 0. 1 is connected to 5, no, we have it 0. 1 is connected to 6, no, we have it 0. Likewise, we will be finding all the values for all the nodes till 6. The diagonal values will be if you see, the diagonal values will be 0 here. So this is the affinity matrix. Then degree matrix. Degree matrix is a diagonal matrix in which we will specify the degree by summing up the rows of the node. For example, for node 1, we will sum up all the values. 0 plus 1 plus 1 plus 0 plus 0 plus 0. Then we will get the degree of this node. So here 1 plus 1 which is equal to 2. So this 2 is the degree of node 1. Likewise, we can find the degree of all the nodes till 6. So we got the diagonal matrix. So we found the diagonal matrix. We found affinity matrix. So then it will be determining Laplacian matrix. So for finding Laplacian matrix, we will subtract affinity matrix from degree matrix, D minus A. we will get the Laplacian matrix. So the degrees will be available on the diagonal, and here minus 1 minus, as we are subtracting affinating matrix from degree matrix. Next thing is a normalized. We form the normalized Laplacian matrix. To find the normalized Laplacian matrix, we use this formula: I minus e to the power of minus 1 by 2 w into d to the power of minus 1 by 2. Here I is the identity matrix, d to the power of minus 1 by 2 is the inverse square root of the degree matrix d, w is the weight matrix. So eigenvalue decomposition. Once we have the Laplacian matrix, we need to find the eigenvalues and eigenvectors to form clusters. So to find the eigenvalues and eigenvectors, we have this formula to determine the eigenvalues and eigenvectors. L equal to u lambda u to the power of t. After obtaining the eigenvectors, we can use various techniques to cluster the data. Here, each row in U represent the data point in a low dimensional space, and we apply k-means to partition these data points into clusters. This U matrix is a matrix of eigenvectors. From that, we will get the clusters. So the advantages and limitations of spectral cluster algorithm. So the advantage is the scalability. It can handle highly complex data set, and it is robust to robustness to noise. It is highly strong, robust to noise and outliers, and it is flexible. As we use only the connectivity between the data points to form clusters, they are flexible. They don't follow any traditional method like distance method to form the clusters. So it is flexible. The limitations of this algorithm is sensitive. It's sensitive to hyperparameters, and there is a computational complexity increases because here we form a graph and then we form a matrix. From the matrix we find eigenvalue and eigenvectors. So the computational complexity